In this module, we will consider rotational motion. The motion of point particles is described entirely by their positions as a function of time. But for extended objects, not only do we need to know their positions, we also need to know their orientations as functions of time. Just as point particles can move with some velocity, extended objects can move and rotate. Every aspect of the translational kinematics and dynamics of point particles has a corresponding rotational counterpart. For example, translational motion is replaced by rotation. Linear velocity becomes angular velocity. Linear acceleration becomes angular acceleration. Linear momentum becomes angular momentum. Force becomes torque. And translational kinetic energy becomes rotational kinetic energy. Even though there are many similarities between translational and rotational motion, we will find that there are some important differences. Many of the vectors we deal with for rotating objects are not normal or rather conventional vectors. They are what are called axial vectors that have a slightly different behavior compared to regular vectors. We're not going to deal with the deep underlying mathematics involved with the difference between axial and conventional vectors, but we are going to see some of their consequences. To keep things reasonably simple, we will consider rotational motion of a flat extended object about a fixed axis perpendicular to the object. Consider a triangle. Let the triangle rotate about an axis of rotation passing through the red dot. If it rotates by an angular displacement of theta, then all points in the extended object rotate by the same angular displacement. However, points at different distances from the rotation axis travel different linear distances. For example, consider the point P1. It travels a particular linear distance when it rotates by an angle theta. However, the point P2, which is further away, travels a longer distance because it is further away. The path traveled by a point on the object a distance r from the axis of rotation will be an arc of length s equal to the angle of rotation times the radius to the point from the rotation axis. This comes immediately from our definition that the circumference of a circle is equal to 2 pi times the radius of the circle. So if instead of traveling the full 2 pi radians around the full circumference of the circle, we travel only a partial distance, theta, around, we get immediately the arc length s being that angular displacement measured in radians times the radius. Given a fixed rotation axis, we find that the angular speed of an object rotating is given by the time derivative of the angular displacement with respect to time. This is measured in units of radians per second, or more usually just simply as inverse seconds. The magnitude of the angular acceleration is given by the time rate of change of the angular speed, or the second time derivative of the angular displacement. It has units of radians per second squared, or simply inverse second squared. Now, linear velocity and acceleration are vectors. There are also vector versions of their rotational counterparts. How do we go about determining in what direction they point? Well, the directions of the angular velocity vector omega and the angular acceleration vector alpha are parallel to the axis of rotation, but this gives us two possible directions for each vector. To break this degeneracy and to determine which direction the angular velocity and angular acceleration point, we use something called the right-hand rule for rotation. We take our right hand and we place it so that we wrap our fingers around the axis of rotation, with our fingers wrapping around in the direction of rotation. Your thumb then points in the direction of the angular velocity, omega. For the angular acceleration, we note that if the angular velocity is increasing, then alpha, the angular acceleration, points in the same direction as the angular velocity. However, if the angular velocity is decreasing, then the angular acceleration points in the opposite direction from the angular velocity. The instantaneous angular velocity vector omega can be rigorously defined as an axial vector. However, the average angular velocity given by the finite change in angular displacement over a finite change in time cannot be associated with a vector. This is a very interesting mathematical detail. The deep reason for what's happening here is the fact that infinitesimal rotations commute. However, finite rotations do not commute. What do we mean by this? Well, to see what's happening here, consider the following. Place a book on a tabletop. And now let's define our coordinate system so we can keep our rotations straight here. And let's first imagine rotating the book by 90 degrees about the z-axis. The result looks as shown in the figure. Now, the next thing we want to do is rotate about a different axis, in this case, the x-axis. We're going to rotate again by 90 degrees, and the result looks like the following. Now, let's do the same two rotations, one about the z-axis, one about the x-axis, but let's do them in the opposite order. So we start with the book in the original orientation. We now rotate first, this time about the x-axis. We get the following orientation for the book. Now we want to rotate by 90 degrees around the z-axis, and the result is the book in the illustrated orientation. By performing the two rotations in opposite orders, we have commuted the order of the rotations. We see clearly that the final orientation of the book is different in the two cases. And this is what we mean by the fact that finite rotations do not commute. Now, we have seen that when the body rotates through an angle theta, a point at distance r away from the axis of rotation travels a particular distance s given by r times the angular change theta. Now, if the body rotates with an angular velocity omega, a point at distance r from the axis of rotation has a linear tangential speed, which is given by the time rate of change of the distance traveled for that point. That is, it's going to be r times d theta dt, which is r omega. Similarly, we find a linear tangential acceleration for that point, given by r times alpha. It's interesting to note that the direction of the tangential linear speed and the angular velocity are never parallel to each other. Similarly, the direction of the linear tangential acceleration is never parallel to the angular acceleration. Now, when we consider a body that is rotating with a constant angular acceleration about a fixed axis, we find that the equations for rotational kinematics are in direct analogy with those for linear motion under a constant acceleration. Each equation has a direct counterpart where acceleration is replaced by angular acceleration, velocity with angular velocity, and position with rotational position. Let's consider an example. Let's take a classic record player and assume that it takes 3 seconds to transition from rotating with 45 RPM down to 33 1/3 RPM. What is the angular acceleration vector, and how many rotations does the platter make during this 3-second transition period? Well, first of all, we need to think about what the rotation is doing. For a record player like this, the platter is rotating in the clockwise direction as shown. So let's see what is the direction of the angular velocity vector. We put our hand on here and wrap our fingers around the axis of rotation. And if our thumb is pointing up, then we see that our fingers are wrapping around in the opposite direction from the direction of the rotation of the platter. So we need to turn our hand upside down, and we see that the angular velocity vector points down into the turntable. Now, we have been given angular speeds, which are in RPM, and we need to convert these into radians per second, or simply inverse seconds. So we write down the conversion rule for this. And so our initial angular velocity of 45 RPM becomes 4.71 inverse seconds. And our final angular velocity, 33 1/3 RPM, becomes 3.49 inverse seconds. And we can use the simple relationship between angular speed and acceleration in time to find the angular acceleration. The angular acceleration is minus 0.407 inverse seconds squared. And this means that the angular acceleration vector points up because the initial angular speed points down and our angular acceleration is negative. It's less than 0. To find the number of rotations, well, we take the relationship between angular displacement and the acceleration in time. We plug in our values for the angular acceleration, and we find that we go through 12.3 radians of rotation, which we can convert into revolutions by dividing by 2 pi. And we find that the platter rotates 1.96 revolutions, almost 2 full revolutions during that 3 seconds. As a final point, let's revisit centripetal acceleration. In addition to any linear tangential acceleration present when the angular acceleration doesn't vanish, any point on a rotating object will also experience a centripetal acceleration, and this will happen even if the angular acceleration is 0. Recalling the definition of the centripetal acceleration as the tangential velocity squared divided by the radius, we wind up with our equation for the centripetal acceleration being r times the angular velocity squared. Interestingly, The directions of the centripetal acceleration, the tangential acceleration, and the angular acceleration are all mutually perpendicular.